Okay. Now we'll see divergence and curl. Divergence and curl. Divergence. Suppose I have some vector point function a bar, some vector point function, then del dot a bar, del dot a bar, we call divergence of a bar, del cross a bar, we call it as curl of a bar. But how is it defined? This is defined as, suppose a bar is a1i plus a2j plus a3k. Then divergence of a bar is nothing but dou a1 by dou x plus dou a2 by dou y plus dou a3 by dou z. అంటే నేను డిఫైన్ చేయట్లా, మీరు డాట్ ప్రోడక్ట్ తీసుకుంటే అదే వస్తుంది. ఓకే, ఫర్ ఎగ్జాంపుల్ డైవర్జెన్స్ డెల్ ఇస్ డో I dou by dou x plus j dou by dou y plus k dou by dou z dot a1i plus a2j plus a3k. Okay, I dot I is 1. Therefore, what I will get dou a1 by dou x will be there. But I dot j 0, I dot k 0. Next, j dot I 0, j dot j 1. Therefore, dou a2 by dou y remains. Like that, dou a3 by dou z also remains. This is divergence. Okay, and this is defined as determinant of I, j, k, dou by dou x, dou by dou y, dou by dou z, a1, a2, a3. Symbolically, we also write it as div a bar. This we write it as curl a bar. Symbolically, div a bar or curl a bar here. So this quite obviously, whatever it comes out to be dou a3 by dou y minus dou a2 by dou zi plus dou a1 by dou z minus dou a3 by dou xj plus dou a2 by dou x minus dou a1 by dou y k. That is curl. Okay. Now let us go with some kind of physical interpretation of this. I'll give a small example, one example here, one example there. Okay. Okay, anyway. So let me go with some kind of a simple interpretation of this. Suppose, I don't know how many of you remember a rheostat. Rheostat in your variable resistor. Electrical wala gurtuntu. Okay. On intermediate law, in +2 level, we have done one experiment in physics. Okay, a rheostat. What is the rheostat? Rheostat has a cylinder, basically. A cylinder. Okay, a cylinder which has some axis like this. on which there is a very thin copper wire is wound on that. Very thin copper wire, very, very thin one. The diameter of that wire is extremely small compared to diameter of the cylinder. So very, very thin wire is wound on that. Suppose this is the cylinder, very thin wire is wound on that. Okay? Now, something like that. Okay? It keeps going, it keeps going. Okay? So, if you see this properly, since the cylinder is very thick cylinder, okay, the diameter is huge one when compared to dimension of the diameter of the wire. So, when it is wound on that, the way the wiring is wound, it will be almost perpendicular to the axis. The wiring is actually perpendicular to the axis of the cylinder. The wiring of this, the way it moves like this, it almost is perpendicular to axis of the cylinder. Okay. Now, suppose if I pass some I current to this copper wire. Okay. What happens? The wire flows like this. So the current flows like this along the wire. Now, there is one principle called as magnetic induction, electromagnetic induction. What happens whenever current flows along a wire? It induces a magnetic field around it, given by right-hand thumb rule. Given by right-hand thumb rule. Suppose this thumb indicates the flow of current. The flow of current, then the closing of the fingers indicate the magnetic field induced around that wire. Okay. So, when the flow of current is like this, then the magnetic field that is induced will be something like this. Okay. The closing of the fingers indicates the magnetic field induced. So, now what happens? Suppose I have a wire like this, current is passing through the wire like this. Okay. So, when I apply magnetic field induction, the thumb indicates the direction of electric field, so current. Then inside the cylinder, if I see, the induced electromagnetic field would be along the axis. Here or here or here or here. At any point on the wire, if you see, inside the cylinder, the electromagnetic field would be in one direction only. That would be along the axis. If you see that. This much of huge cylinder, suppose I have a wire like this. Okay. When I have a wire like this, current is passing through this. Inside the cylinder, if I see, electromagnetic field induced will be going along the axis. Here, along the axis. Here, along the axis. At any point, if you see inside the cylinder, the electromagnetic field would be, the induced electromagnetic field would be along the axis. In fact, that's what we call it as, all this electromagnetic field converges along the axis. Converges along the axis. That means the divergence is zero. There is no divergence for that. There is no divergence for that. That means whenever divergence of A bar equal to 0, we have some kind of convergence into one axis, that is also called as solenoidal. In fact, this is called a solenoid. The wiring, the wounding of the wire on that cylinder, we call it as a solenoid. And the field A bar is said to be a solenoidal field if divergence is 0. That means we have complete convergence in the solenoid basically. Okay. So, such a field we call it as a solenoidal field whenever the divergence is equal to 0. So, this is one place where we have the divergence equal to 0, we call it as a solenoidal one. We have lot many examples of solenoidal fields, but I have taken this specific example because everyone knows that this is a solenoid and we know what is a rheostat and we know what is a cylinder and current. Okay. Let us come here. Curl. The term curl itself indicates there are some kind of rotational components in the rotation. I will give a small example of rotation. Suppose I have a bucket of water, or maybe you can take a tank of water also, bucket of water. So, this is bucket of water. Okay. What I do is I give on the top surface of water, I give rotational forces to the top layer. Okay, I keep rotating it. Okay, I keep rotating it. When I keep rotating it, what happens here? The top layer is rotated. Okay, maybe clockwise or anti-clockwise, whatever you feel like. Okay, when you rotate clockwise or anti-clockwise, what happens? The top layer gets rotated the way your hand or fingers rotate. Okay, now that means actually I am passing some energy to the top layer. That gets transferred to the lower level layers of water. Okay, when it gets transferred, since it is a mechanical energy transfer, there is always loss of some heat, loss of some energy. Okay, then loss of energy is there means that the total amount of work that would be done would be less. On the lower levels, the total force would be less. Therefore, it keeps coming down, coming down, coming down, coming down. So it forms something called as a vortex. This is called as a vortex. When do vortex appear? Whenever you have rotational components. Whenever you have rotational components, vortex appears. Suppose you don't have any rotational components. You don't have any rotational, we call it as irrotational. Irrotational. There are no rotational components. Irrotational when the curl equal to 0. Curl means rotatory components are there. When there is no curl means it is irrotational. That means you do not, it doesn't form a vortex now. When it is irrotational, it doesn't form a vortex. When you have rotatory components, only then vortex can be formed. Are you getting that? And that too, you need to have consistent flow of energy here, or else you cannot have a vortex also. Once the flow of energy stops, vortex also stops. That's what it is. Okay. So whenever it is irrotational, curl equal to 0. Whenever it is solenoidal, divergence equal to 0. And one more thing, whenever it is irrotational, curl equal to 0 means it's a vector. It's a vector actually. Vector equal to 0 means each component of the vector has to be 0. So this is 0, this is 0, this also is 0. Are you getting that? So each component is equal to 0. Now I will try to represent this later on in a different context. So try to remember that curl equal to 0 means it is irrotational. And each component of the vector will become equal to 0 also. Okay? Okay. This is called curl.